Good morning, dear students. Just recall what we have discussed in our last class. Last class we have discussed about Zn. The elements are 0, 1, 2, etc. n minus 1. Everything is congruent class moduli. Okay. Now and finally we have discussed about multiplicative inverse of A. Okay. And the definition is good morning, dear students. Just recall what we have discussed in our last class. We have discussed about Zn and we have discussed some properties like addition and multiplication in Zn, and we have proved that operations are well defined. Okay, and we have discussed some properties like additive inverse and multiplicative inverse. Now, the definition of multiplicative inverse also we have discussed zero divisors. Okay, an element A is said to be is called a zero divisor if there is some B such that non-zero such that this is equal to 0. Then we call A is a zero divisor. Clearly, B must be not equal to 0. Okay, and finally we have discussed multiplicative inverse. So if an belongs to congruent class modulo n belongs to Zn and an bn is equal to 1, ab equal to 1. I am just using ab. You must understand that is a congruent class modulo n. Okay, ab equal to 1 for some congruent class b, and then b is called multiplicative inverse of a. Okay, and it is denoted by A inverse. Now in this case we say that An is invertible element of Zn, or in this case we call it is a unit of Zn. And also we have discussed one problem and here and that was set. Okay, and we have proved 1 inverse is 1 and 2 inverse does not exist, 3 inverse is 3, because we are actually looking for the row containing 3, and where 1 comes, that is the inverse of this element, that here inverse is 3. Okay, so here there is no entry as 1, therefore it does not there does not exist any inverse for 2. And but if you look at 2 into 2, clearly 2 not equal to 0, but if you multiply this both we get to 0. That means 2 is a 0 divisor. Okay, so 2 is a 0 divisor. Now next I am considering set 5 and operation multiplication dot, here dot. Okay, and in final we have denote this operation as multiplication model of multiplication 5, that we will discuss later. Okay, so here we are using the notation just multiplication as dot. Okay, and this is the table for Z5. You can verify it, and from table actually we are evaluating inverse for non-zero element. What about 1 inverse? Here 1. Okay, 1 is here, so 1 inverse is 1 itself. What about 2? 2. Okay, and you just look at where 1 happens, and here is 1, therefore 2 inverse is 3. And what about 3? 3, here 1, that means 3 inverse is 2. And what about 4? 4 inverse is 4 itself. So here inverse exists for all non-zero elements. Here inverse exists only for 1 and 3. Now I am considering Z6. Here again, if you look at 1 inverse is 1, 2 inverse does not exist, 3 inverse does not exist, 4 inverse does not exist, 5 inverse is 5 itself. So clearly if you multiply 2 and 3, 2 and 3, here we get 0. That means 2 and 3 are 0 divisor. Okay, 2, 3, 4 are 0 divisor or divisor of 0. So here inverse exists for 1 and 5. Here inverse exists for 1 and 3. So in Z3, inverse exists for 1 and 3. In set 5, inverse exists for 1, 2, sorry, set 5, 1, 2, 3, 4. And in set 6, inverse exists for 1 and 5. In Zn, which elements must have inverse? This is actually 1. Okay. From this, can you recognize? Is there any property between 4, 3 and 1? 5, 1, 2, 3, 4. 6, 1 and 5. Just think. Does there any relation? In this case, 2. Inverse does not exist. In this case, 2, 3, 4 does not have inverse. Does there exist any relation between these numbers and number 6? Or does there exist any relation between these 2 and this 6 number? Just check. Once again. Once again. Yeah, these two numbers 1 and 5 are relatively prime to 6. Here 1 and 3 are relatively prime to 4. Here 1, 2, 3, 4, 5, 5, 1, 2, 3, 4 are relatively prime to 5. But 2, 3, 4 are not relatively prime to 6. Here 2 is not relatively prime to 6. Therefore, inverse exists only for those elements that are relatively prime to n. That means those elements that are GCD 1 with n. Okay, that is our next theorem. Our next theorem is let n be a positive integer and the congruent class an has a multiplicative inverse in Zn if and only if a and n are relatively prime. That is if and only if GCD of a and n is equal to 1. What is the GCD? Suppose a and n is equal to some d. What is the meaning of that? There exist integers q and r such that this is equal to rn is equal to d. Okay. If there exist integers q and r satisfy in this condition, that means GCD of an is equal to d. Okay. So GCD of an is equal to 1 implies 1. There exist integers p and q such that qn is equal to 1. Okay. So now next is B part is a non-zero element of Zn either has a multiplicative inverse or is a divisor of 0. Okay. From this example it is clear. Okay. 1 and 5 is relatively prime to 6 and 2, 3, 4 is a divisor of 0. Okay. So now moving to proof of this proposition 1.4.5. First what we have to prove? We have to assume that the congruent class has a multiplicative inverse and we have to prove GCD of A and N is 1. That is GCD of A, that is N is A is relatively prime to N. So first we assume that this has a multiplicative inverse. And let this inverse be B. What is the meaning of that? A inverse equal to B means, by definition, A inverse equal to B means AB equal to N. Sorry, AB equal to 1. Okay. Okay. Clear. So now what is the meaning of AB? AB is, by definition, AB is same as AB. So AB equal to 1 means AB equal to 1. AB equal to 1. That is actually AB and equal to 1. What is the meaning of that? AB is congruent to 1 mod n. Okay, AB is congruent to 1 mod n. AB is congruent to 1 mod n means what? AB minus 1 is a multiple of n. That is AB equal to 1 plus qn. Or AB plus minus qn is equal to 1. There exist integers this and this such that b into a plus this integer into n is equal to 1. That means GCD of a and n is equal to 1. Okay, that means a and n are relatively prime. Now conversely assume that a and n are relatively prime. That means there exist integers b and q such that ab plus qn is equal to 1. That is AB equal to 1 minus Qn or AB equal to some 1 plus Kn. K is equal to minus Q. Or AB minus 1 is equal to Kn. That means AB congruent to 1 mod n. AB congruent to one mode n implies congruent class AB is equal to class 1. This implies A inverse is equal to B. Okay, so that is the proof. Now what we have to prove? We have to prove next a non-zero element of Zn is either has a multiplicative inverse or a divisor of 0. So that is what we have to prove. Suppose, okay, so if it is relatively prime, then clearly it has a multiplicative inverse. There may be two cases. A non-zero element in Zn. What is actually Zn? Zn is 0, 1, etc. n minus 1. Okay, so if you take any A belongs to Zn, we have to prove either A is a zero divisor, everything n. Okay, either A is a zero divisor or A is a multiplicative inverse. Okay, so if you consider A, if A and n, GCD of A and n is equal to 1, then A is relatively prime to n. That means it has a multiplicative inverse. Suppose this GCD is not equal to 1. That means A and n is equal to GCD of A and n equal to D, where D not equal to 1. So what we have? We have A belongs to, from this clearly A is less than n. Okay. A is less than n means clearly n does not divide A. Okay, n does not divide A. N does not divide A. Okay, so this is equal to D means A, and that implies what happens there in this case. If A and n equal to D, where C1 less than D less than n. Okay, in this case, since D divides n, because D is the GCD, D divides both n and d. Okay, since D divides n and D divides A, what happens? D is the GCD, that means D divides A and D divides n. So D divides n means n is equal to some k into D. Similarly, A is equal to some b into D. Okay. So we have this. N is equal to k into D and A is equal to b. Now k is a non-zero element of Z. Okay. Now, but what is AK? AK is equal to AK, but A is BDK, and KD. What is KD? KD you can write as BN, but BN, this is a multiple of n, therefore this is equal to 0. So A into, K is a non-zero element in Z. Okay, so a into a non-zero element must be equal to 0 means A is a divisor of 0. Okay, once again, if A represent non-zero congruent class, that is n does not divide A. If A, GCD of A and n is equal to 1, then clearly A has a multiplicative inverse. Otherwise, suppose A and n is equal to D, where D is clearly 1 less than D less than n, because D is a divisor. GCD means greatest divisor. So clearly this D must be strictly less than n. In this case, since D is a divisor of both A and N, D divides N and D divides A. That means we can find integers K and B such that N is equal to KD and A is equal to BD. Okay. Now, clearly this K is a non-zero element of Z. Okay. So, what we can write? We can write like this. This implies A is a divisor of 0. Hope it is clear. Okay. Now moving to one corollary. The following conditions on modulus are equivalent. That means what we have to prove? We have to prove 1 implies 2, 2 implies 3 and 3 implies 1. Okay. The number n is a prime. Zn has no zero divisors except 0n. every non-zero element of Zn has a multiplicative inverse. Suppose n is a prime. So if you consider n is a prime, Zp. Okay. So what about Zp? Elements of Zp 0, 1, etc. up to p minus 1. Clearly 0, 1 to etc. p minus 1 are relatively prime to p. Okay, so using previous theorem, every element of Zp has a multiplicative inverse. Also, Zn has no divisors of 0 because by previous theorem, 0 divisors are those elements that are not relatively prime to p. Okay, here every element are relatively prime to p. That means it does not have a 0 divisor. It does not have a 0 divisor. Okay, then clearly every element of Zn has a multiplicative inverse. Zn has no 0 divisor means every element is as a multiplicative inverse. Now, suppose every non-zero element of Zn has a multiplicative inverse. What is the meaning of that? Suppose if we consider Zn, that means 0, 1, etc. n minus 1. Every element has a multiplicative inverse. Means if you take any A belongs to this representative A and GCD of A n is equal to 1. For every A from 0, 1 to etc. n minus 1, if this condition holds means n is a prime number. Okay, so 3 implies 1. Okay. Now we have to find how we can find an inverse of an element. Suppose if you consider some set 7, what about inverse of some 6 or inverse of 5? Actually, what we have done in our this case, we are just looking through the rows and we will check where the one comes first. Okay, that's what we have done. So that is the same procedure. Okay, actually what here 5 into 5 1. Okay, so here for finding inverse, what we are doing is if you take any, if a and n is GCD of a and n is equal, then only inverse exists. Okay, that means a is not a divisor of 0. A is not a divisor of 0 means if you take any power of a, that never be 0. And we let a raised to 0 is equal to 1. This is we are assuming. We let a raised to 0 equal to 1. Then take all the powers 1, 2, power 1, power 2, 3, etc. And at some point, these elements may be repeat. Okay. And we will check where the first repeat happening. Suppose let it be m. That means a raised to m equal to a raised to k with k less than m. Okay, so that means a raised to m equal to a raised to k. Okay, that means a raised to m minus k equal to a raised to 0 and a raised to 0 is 1. Okay, that means since we can cancel both sides. Okay, so this implies what happens actually. We have a raised to k must be this first repetition. When this first repetition holds, this happens only if k equal to 0. That is, we get a raised to m is equal to 1. Okay. From this we get a inverse is equal to a raised to m minus 1. There is no need to study all these things. Okay, just understand the process and you have to remember only one result. A inverse is equal to a raised to m minus 1, where m is the first integer with a raised to m is equal to 1. Okay, so this must, you have to remember this. A inverse equal to a raised to m minus 1, where m is the first integer with a raised to m equal to 1. Using this, we are trying to find one problem. Find 11 inverse in Z16. 11, 16 inverse. So what we have to find? We have to find powers of 11 and we have to check at which power 11 raised to m is equal to 1. So if you consider 11, 11 square, 11 square, what is 11 square? 11 into 11, and which is equal to 121 over 16. Okay, and this is equal to 960. Or you can easily say 11 is same as how we will get 11 and in terms of 60. If you consider minus 5, what is minus 5? When we add something with uh, 16, we must get minus 5. Okay, inverse of 5. That is, if you add 5 plus 11, then clearly we get 0. That means from this we get 11 inverse is 5. Similarly, 5 inverse is 11. That means 5 inverse means additive inverse. Minus 5 is 11. So you can also use this property. Minus 5 minus 5 is minus 5 minus 5 is 25. 25 is if you take 25 mod 16, that's equal to 9. Or you can directly do this like this. Then evaluate 11 cube. 11 cube is 11 square into 11. 11 square is 9. So 99, and which is equal to 3. Because you evaluate 99 divided by 16. Okay. Calculate this. Then we will get 3. Now 11 raised to 4 is like this, and we get this one. That means 11 raised to 4 is equal to 1. That means 11 inverse is 11 raised to 4 minus 1 equal to 11 raised to 3, and 11 raised to 3 is 3. So 11 inverse is 3. Okay. Now moving to next definition, let n be a positive. This is very important. Let n be a positive integer. The number of positive integers less than or equal to n, which are relatively prime to n, is denoted by phi of n. The number of positive integers less than n and relatively prime to n is denoted by phi of n. For example, phi of 4 is number of integers less than 4 and relatively prime to 4 is 2. Which are the 1 and 3. Similarly, phi of 5. What is phi of 5? Sorry, phi of 5. 1, 2, 3, 4. Okay. So phi of 4 is, phi of 5 is 4. Number of integers relatively positive integers less than or equal to n and relatively prime to n. Okay. So, and this function is called Euler's phi function or Euler's torsion function. Okay. So now we have here one proposition. Proposition is, if the prime factorization of n is like this, p1 raised to alpha 1, p2 raised to alpha 2, etc., pk raised to alpha k, where alpha I greater than 0, then phi of n is, this is very important. You just recall this formula. Phi of n is n into 1 minus 1 by p1 into 1 minus 1 by p2, etc., 1 minus 1 by pk. p1, p2, etc., pk are primes in the factorization. For example, if you consider n is equal to 6, and you can write as 2 into 3. So p1 is equal to 2, p2 is equal to 3. And if you consider n is equal to 8, then n you can write as 2 raised to 3, and here p1 is equal to 2. And phi of n is n into 1 minus 1 by p1. Here p1 is 1 by 2. That is 8 into 1 by 2. That's equal to 4. So phi of n is, here phi of 8 is 4. If you consider 8, what are the numbers relatively prime to 8? 1, not 2, 3, not 4, 5, not 6, 7. Okay, so here 4 in number, therefore you can easily evaluate using this formula. Okay, you try to do this 17, 29 as homework, and 30 is also there, but you first try to prove 17 and 29 and do this as a homework. Only after completing homework you submit your notes. Okay, now using this formula, phi of 10 is 10 into 1 minus, because 10 you can write as 2 into 5. So 1 minus 1 by 2 into 10 into 1 minus 1 by 2 into 1 minus 1 by 5. That is 10 into 1 by 2 into 5 minus 1, 4 by 5. And we will get 4. Similarly, phi of 36. You can write like, and it is equal to 12. Now moving to last definition. The set of units of Zn, the congruent class A such that An is equal to 1 will be denoted by Zn multiplication. Okay. Units in Zn is denoted like this. Okay. Now what about units in set 4? Units are 1, class 1 and 3. Okay. Units in set 6, 1 and 5. Okay. Okay, that's all for today.